People who have logged in, you can please rename yourself in the format college, your name, faculty or student, department. Please rename yourself.
Gopinath, Kavin, Nivashini, anybody let me know you are from which college? All your roll number are similar.
Good afternoon, Robin.
Co-host you second.
Good
Thank you.
afternoon, ma'am.
Afternoon. ஒருத்தரா
Students,
பேரை கேட்டு எழுதணும் போல இருக்கு.
students from Nanda College logged in.
This is Realme C2. அவர் யாரு? பால்ஸ் பிஜிஎம்ல இருந்து தான் நிறைய நாய்ஸ் வருது, பேக்ரவுண்ட் நாய்ஸ். பேக்ரவுண்ட் நாய்ஸ். கதவு ஜன்னல் ஏதாவது திறந்திருந்தா ப்ராப்ளம். That's better. It's a different kind of name. Pralaya Kaveri Siva.
Fine now, ma'am.
Yeah, now it's better. Why are they putting their student ID or something? 20A and all that. 20A, GO05,
The
GO11.
roll number it seems. That's why I asked.
Hmm?
All the students kindly display name in the format which is given in the chat box. Rather than mentioning your roll number, kindly change in the given format.
Or at least prefix it with your college name so we will know the college.
மேடம் ப்ரொஃபசர் கால் பண்ண சொல்லியிருக்காரு 255க்கு.
கூப்பிடுறீங்களா?
நான் கூப்பிட்டுறேன்.
சரி
ஆல்ரெடி பேசிட்டேன் காலையில.
சரி சரி
எனக்கு ஒரு 2:55 கால் பண்ணிருங்கன்ட்டாரு.
சரி, அவ்வளோதான் டைம் அதுக்கு. பிகாஸ் அவருக்கு நிறைய ஸ்டூடெண்ட் கவுன்சிலிங் போயிருக்கு.
அதான் அதனால நான் வந்து பிஸி ஆயிருவேன்.
ஆமாம், மறந்துடுவார். தான் சொல்லிட்டு கூப்பிட்றேன். People have written. Nobody has typed in. Na? Gopinath, you have to name yourself as Nanda, Gopinath, and student or faculty, whatever. And if possible, your department as well. That would be useful information. Gopinath? எல்லாரும் ஆன் பண்ணிட்டு போயிட்டாங்க. பயங்கரமா இருக்குது.
Students, requesting you to kindly rename your Zoom display name. Good afternoon, Arundev sir.
Hi, good afternoon, Varuna. Good afternoon.
Good afternoon, Arun.
Hi, Anu. Hi.
Good afternoon, Arun sir.
Hi. All of you. I know there's a query on the 9th T2P subject.
Okay. It's he said he will finalize and send it today. Today it will be coming up. Innovation or whatever.
Okay.
MS Srinivasan. I spoke to him.
Oh, you spoke to him. Good.
He said he will send the abstract and everything today. I'll remind him.
The last time he came to VCW, that person.
Yeah. He has come to Dhanalakshmi Engineering College also once. When Thiru was there. So he remembered all that.
Anu ma'am and Arundev sir, for information, we are live in meeting.
Okay.
Yeah.
I think you need to announce once again because
Yeah.
nobody has
Once
changed.
we start, I will give the announcement.
And இது என்ன class? Who's asking that?
Gopinath, ma'am. Come on.
Gobinath, this lecture is called Theory to Practice lecture. There's a professor from IIT who's going to be talking to you all. He's going to talk about visual analytics with self-organizing maps. So I also don't know what it is about, but he's going to talk about how theory is applied in practice. So he'll naturally talk both about the theory and how it is used in real life situations. It may be useful for presenting information in a visual fashion, is what I guess.
All of these students from first year, it seems, ma'am. That's why they are asking.
Okay, first year. Okay.
Yeah, first year.
Which college is this from?
Nanda. The roll number students. They
Oh,
mentioned the roll number.
okay. Uh, because you are just in the first year, some of these information which are given may go overhead, but don't worry about it. Have a keen listening to it if you are just in the first year. He may touch upon all basics as well. Never shut yourself to the information which is given to you. Okay? There will be a small test towards the end, so it will be good if you can take down some notes. Multiple choice questions only, no negative marks. So are you all attending classes live these days? Are you coming to college?
No, they won't be able to unmute and
Chat,
speak.
but they can chat.
They can chat, yeah.
I find Mr. Balamurugan, faculty from KSR IET attending. Welcome, sir. Mm,
And ma'am, there is a response in the chat box.
yeah, I'm trying to, what is it? No, ma'am, we are attending classes through online. Okay. Celine. Celine, can you rename yourself according to the format given? Or they have to record their attendance, no? Whatever. Are the first semester exams over? Hmm. Kirtana Kirtika Kritika. There's some sound like, or is it only for me, Lavna? That's
Yes, ma'am. I didn't hear anything.
you don't
Robin
hear.
sir or Sujata ma'am, are you hearing anything?
No.
Maybe
Yeah.
this is so sensitive. No, it's not there. All the 20 years are first years of Nanda, is it?
No, ma'am. Few KCG and some other colleges are there.
VCW is there.
Yeah.
Look for faculty names. Welcome.
Robin, have you reminded Professor?
Yes, just now.
Okay.
He said he will log in at 3.
Meanwhile, KCG College had a lot of registrations. I saw some 63 or 65 registration.
100, ma'am, finally.
Yeah, so if there is any faculty of KCG or any students who could, give a reminder to your fellow mates who have to join and kindly do that. Because we saw close to 100 registrations and there are only 4 of you here, I see. 4 or 5.
into. Okay. Anu, ma'am, you are muted.
No, Pulse PGM, when not in use, you put it in muted because I hear a lot of noise.
Is it, ma'am? I am wearing headset. Not sure.
Yeah, when you're not talking, you mute
Yeah,
it.
yeah. Not sure. There is no noise from my side. Sujata, ma'am, are you also hearing the same? Do you want to remove my headphones?
Lavana, professor has joined.
Co-host.
Good afternoon, Professor. I have made you as a co-host. You can unmute and unmute, sir.
Yeah. Shall we start? It's one
Good
more minute.
afternoon, Professor
Good
PALANIAPPAN
afternoon.
RAMU.
We're not able to hear him.
Yeah.
We have to say ask to unmute.
Can you hear me now?
I
Yes,
can
sir.
hear. Yeah, we can hear you.
Yeah. So
Good.
I was just trying to, Okay. Just give me a minute because I'm trying to do this on my iPad so that I can scribble on the thing. And I'm just roughly how many participants are there?
How many registered? And right now we have 40.
Okay.
We have
And
close to 250 to 60
250.
registrations, Professor.
oh, I see. Okay.
And we have also streaming it on the YouTube, so there
YouTube.
could be live watchers in the YouTube channel as well.
Well, that sounds okay, but okay. All right.
They should be able to chat and provide answers. And I would request the PMO to have a look at the YouTube channel as well in case they are giving any answers there.
Okay. So are you able to see my face? You're not able to see my face, are you?
No.
Your
Okay,
video
good.
is not yet turned on. Yeah.
Can I maybe in the beginning I'll keep it open, but
Yeah,
after that what I'll do is I'm going to keep the pad flat. So I'll share. So let me make sure that share content.
Content, yeah.
Let me share my screen. Okay.
Yeah.
So just 1 second. You are able to see my screen, right?
Yes.
So it says visual analytics with self-organizing maps and all that.
Yes.
Okay, nice. So let me just go back to the screen. Okay, probably I should stop sharing. Okay, should I start?
Yes.
Just
we'll
give
do
us a minute, Professor.
1 minute to welcome everybody who are already here just before time. Thank you for being there. And thank you very much, Professor, for being with us. And I know your time is precious, but a quick introduction from Sujata.
Yeah. So good afternoon, all. It gives me a great pleasure in inviting Professor Palaniappan RAMU, speaker for the day. A brief profile of him. I'm sure all of you would have read it in the mail, registration mail that I had shared. Dr. Palaniappan RAMU, he holds a Bachelor of Engineering in Mechanical, which he completed from the Kamraj University in Madurai, and post that a PhD in Aerospace Engineering from University of Florida. Prior to joining IIT Madras, Professor worked as a postdoctoral research associate at the University of Notre Dame and as an optimization engineer at Caterpillar Campaign Simulation Center as well. So he has been the faculty of Engineering Design Department in IIT Madras from 2009. He teaches graduate and undergraduate courses in the areas of design for optimization, finite element analysis, probabilistic and statistical techniques in engineering design. Apart from all the academic accolades that I have mentioned, he also finds time to keep himself fit by taking marathons and triathlons, is what I have heard from our discussion. So it is a privilege to hear from you, Professor. So we welcome you once again. Over to you to start the session.
Yeah. Thank you very much for the great introduction. But a small correction, the first part and all is perfectly fine. Aspiring marathoner or a triathlon. I do practice yoga, but not a marathoner yet. I do half marathons. Yeah, anyway, that's more on the personal side. All right. So let me just... So thank you all for who have showed up for the talk, and I hope I can live up to your curiosity on what this could be. Okay, so let me just go to. So what I suggest is if any of you are not following something that I'm explaining, and you think that it might help for you to understand that, so to maintain the thread. Please don't hesitate to unmute yourself. Can they unmute themselves?
No, Professor.
No, Professor, they wouldn't be able to unmute themselves.
Okay, so then you can chat. That is a problem with a large class. So what you do then is you chat, and then towards the end, I'll take all questions. If there are critical questions in between, whoever is a moderator can please interrupt me, and I'm perfectly fine with that. Okay. Okay, that's the least we could do in this online stuff. If I'm lecturing live, the scenario is entirely different. I practically capture each one of your face and your, like how much you understand and all that. But right now, it's just like cruising on the highway. I have no feedback, so I'm going to keep going. And if it's so bad, please put something like undercode, stop, explain, something like that to the coordinator so that they will let you know. Okay. All right. So
86
start.
on board.
All right. So okay. Fine. So the topic that I'm going to talk about today is visualizing data. Is my screen visible to you?
Yes, Professor, we can able to
So
see that.
it says visual analytics with self-organizing maps. Are you able to see that slide?
Yes, sir.
All right, fine. Awesome. So there is something that they didn't tell in the introduction. It is about the lab, the team. Our lab is called as ADOPT, ADOPT, where A stands for advanced, D for design, O for optimization, P for probabilistic, T for techniques. So it's advanced design, optimization, and probabilistic techniques laboratory. So whatever we do in the team, it's basically got to do with probabilistic techniques along with optimization. Most of the times we deal with design, but of late we have also started looking at not necessarily design, purely from a data perspective also. The one that we are going to present today is a key contribution from this lab. We parallelly pursue multiple works in this where we are trying to visualize data. So there's a lot of data, or there's sparse data, it doesn't matter, because the context that I'm going to talk about will be sparse data. Oftentimes there is more intuition if someone can visualize the data. When I say visualize the data, it is okay to visualize the data in 2 dimensions. The moment my data is greater than 3 dimensions, there's no way that you can visualize the data. It's just a set of tables. So you cannot plot and see that. However, if there is a way that I can represent my data in a visual sense, then it permits intuitive decision making. So this is something that came to us through the collaborations that we have with our industry partners. So we work predominantly on something called optimization. As you all might know, optimization means minimizing something or maximizing. For instance, minimizing weight or maximizing your profit with the same resources. That is called optimization. We collaborate, we advise industry partners on the techniques that they can use in their product domain. One of the usual stuff that I hear from them is, you know what, we don't want that single value that you give us as optimization. If you come back to us and say 12.2 mm for a gauge thickness, I'm not going to be able to manufacture that. I either manufacture 12 or I manufacture 14. These are the standard gauge thicknesses that are available for us. So many a times, the process of optimization and attaining the optima is more, the process of optimization for attaining the optima is more important than finding the optima itself. Because the optima is 12.2, so I really cannot use it. Instead, what is important for me is what happened to my design variables, what different combinations did they tick, why did it go from 13 to 12, why did it come from 14 to 13, or why did it not go to 11, it instead came to 12. This is in terms of the design space that I'm talking about. That iteration history or the physics behind that iteration gives me a lot more information. What they usually call the sweet spot. In the industry, they use this word called sweet spot. It's sweet from different perspectives. It's sweet from robustness. It's sweet for the reason that it gives them what they want, better efficiency. Okay. So the point that they told us over the years of collaboration is, all that I want to know is what direction is my response going to increase if I'm going to change the gauge thickness? If I'm going to reduce the gauge thickness, will my response go, will it increase or will it decrease? That's fair enough. And if you can give me a ballpark number by roughly about 10% is what it's going to increase or it's going to decrease, that's fair enough. In addition to this, another problem that they were seeing is there are a lot of senior people, forget about there are senior engineers, there are senior designers, right? Over the years, they've accumulated a lot of this design experience. But the point is, when they want to do this knowledge transfer to a younger person, it's almost practically impossible. But at the same time, it doesn't make sense for this young person to wait another 40 years in the same company to generate or to accumulate the same sort of knowledge. So one thing what we understood is, when we interviewed these senior designers, they said it's almost like visualizing the design space, but I'm not able to convey this to them because I cannot show greater than 2 dimensions. Even projections, it is left to the imagination of each person. Imagine that there is the design space is 5 dimensions, x1, x2, x3, x4, x5, right? So there is no way that someone can represent or show a point in 5 dimensions. So what they were saying is, many mathematical formulations and functions, the lack of understanding comes from the fact that you are not able to visualize it. Because as you can see, most of you or all of you are from engineering colleges. Many times when you are taught concepts, whether in engineering, mathematics 1, 2, or in any of the physics-based courses, let it be electrical technology or mechanisms of machines, or what else, like strength of materials or analog and digital circuits. One of the first things that as teachers do, or even in the textbook, is you have a picture. So that's essentially permits the visualization, but we also have 2 pages of theory surrounding the picture, right? So those are the explanation, and the picture is just used as an aid. So this is where we got this idea. Oh, it will be fantastic if I can translate this data into a visual mode so that people can see. So now elections are going to come up, right? So now you will start looking at any of the news channels. They will start showing some sort of bubble chart. They will show you take any newspaper today, they will show who has a stronghold. There will be multiple color, green, orange, yellow, red, blue, whatever colors. You see a lot of bubbles, or you see bar charts. All these are statistical data representation. Why? Can't they write it in text? Yes, they can. But sometimes visualization is awesome. You can look at it, you get the gist of it. Okay. So this is where the whole game started. And what we wanted to do is essentially visualize the design space so that a designer, irrespective of the dimensions of the design space, should be able to see how the response varies, where are the sweet spots in the responses, and they should be able to make a decision. And this decision can be at any point of your product design. It could be during the conceptual design stage, it could be in the detailed design stage, it could be in the towards just before manufacturing, at all. So we wanted a unified visualization technique, sort of. Okay. And the technique that we use, there are a lot of techniques, but this interesting technique that we use is called a self-organizing map. It is a unsupervised learning artificial neural network, a branch of that. Okay. And before I start, I would like to thank the students who have directly contributed to this work. Siddhant Tole is the first one to get started to work on self-organizing maps with me. He was the one who formulated and implemented the first modified, what we call the interpretable self-organizing map concept. And Deepak is currently taken the baton from him, and he's working on how to use this to look at Pareto friends, which is a trade-off curve, and how to use this to perform something called a robust design, and several other stuff. Yogesh was an intern with us a couple of summers ago. He's a student from NIT Trichy. I guess he's finishing up. He worked on one of the modules of SOM in its early stage. He was pretty impressed. We were also impressed with him, and he was looking for opportunities to continue to work with us, and he's continuing to work with us. Siddhant got placed in a company called ZS Associates. And my affiliation, I'm from IIT Madras. I am an associate professor in the Department of Engineering Design. This is going to be the outline of my presentation. First, I'll talk about the background. I already gave you a little bit of a background, but I will elaborate a little bit more on that. Then we will talk about what are the state of the art in terms of the visualization techniques. The next one that I'll talk to you about is the conventional SOM, which is what people have used over the years. And we use something called an interpretable SOM. That's the SOM version that we have proposed. Finally, we'll talk about some numerical examples and different applications. So this is the background. Just like any other engineer, we are also interested in y equals f of x. I know that there are a lot of you from different colleges and from different backgrounds, but this one equation unites us all. Y equals f of x. Here, the typical way of looking at this is x is an input. It could be a vector. It could be x1, x2, x3, x4, x50, x100, whatever it is. And y is your response. This is the terminology that I'm going to use during this talk. And f is a function that relates to y and x. Now I'm going to talk about y equal to f of x in a design sense. What do I mean by design sense? So let's say that you are talking about a two-wheeler on an automotive design or a car design. So I'm usually interested in the efficiency of the engine. I'm looking at how many kilometers per liter, especially given the petrol cost right now, right? I'm talking about an IC engine, okay? Even in an electric engine, how far with a single charge? Okay? Now, there are several factors that affects this output Y, which is the efficiency. It can be like the quality of the petrol. It can be the type of the rider. It can be the batch in which the engine was made. It can be the operating temperature of the place that you live. It can be the number of potholes in the street or in the roads that you drive. How many times someone uses a clutch and the brake. There's so many factors, right? So these are all the inputs X, and your output Y is the response or the efficiency that we are talking about, right? So F is a function that relates these two. Imagine that you have a black box function wherein you give all these X and it will give you a Y. Okay. This is what essentially a doctor does with diagnosis, right? The doctor asks, okay, what did you do? Did you check the temperature? Did you check your BP? And thanks to COVID, they will put a pulse oximeter and try to look at what your SpO2 levels are. Now, these are all the inputs. For what? There is an invisible model in the head of the doctor. So these inputs go into it, and the doctor is just going to map and say, hey, you know what? You are fine. Because these numbers mean nothing. Your vitals are fine. It's just a random flu. Okay, you'll be fine. Just take rest. Don't keep staring at your cell phone. Detox, digital detox, and you'll be fine. So essentially, X is an input. F is this relationship between Y and X, and Y is your output, or an example that I gave you is efficiency. When I'm trying to design something, many times I don't even know how many factors are there. Okay. For instance, I gave you an example of the two-wheeler or a four-wheeler, and I just gave you a few examples like 5 or 6 factors, right? But many of these factors are not controllable, or they are not within your control. And there could be like infinite number of factors. But then what we do is we bring them to what we call the trivial factors. Non-trivial factors. From trivial factors to critical factors. So once you boil it down to that extent, that is what is the first block, x1, x2, because beyond that I cannot show. Now what happens here? See this guy out here? That's called the bound of x1 and x2. Many a times we only know the bounds of x1 and x2. If I know only the bounds of x1 and x2, then what it means is this is my entire design space. I don't know anything else. I just know here are the variables and y, which is my efficiency. Now, if I suddenly say, okay, I'm going to put petrol in this place and I am this sort of a driver, can you tell me how many kilometers per liter I will? No, because you don't have a closed form function to tell you that. You don't know what form is this f, the function f is. If you know that, if it says like 3x squared plus 22x minus 3 exponent raised to x1 plus x2 divided by 2, then you can do, but you don't have that many times. Then what happens is someone wants to know, hey, so I want to know what this could be. One thing that you can do is assign a person, assign a vehicle, go put petrol at that place, assign a person who is similar to the driver that they told, and drive it for this much time, and then find out what the kilometer per liter is. But the catch here is this is expensive. Now imagine that you're doing a car crash, or you're looking at a bird impact on an aerospace engine. Why I'm giving these two extreme cases are, when a bird impacts an aircraft engine, the engine is done. It's lived through its life. That's it. You cannot reuse it. When a car crashes, I'm not saying that it was just involved in an accident, it hit someone. When the car crashes, typically you'll have to throw out the car or you'll have to redo the frontal part. Which means the cost of the car is gone. Okay, you are at least accumulating 50% of the car cost, at least. Okay? Now these are expensive because I need to do several combinations. Because if there are 5 factors, you know how many different combinations I can have. So I cannot waste those many cars in reality. Imagine there's a BMW and the price is 75 lakhs. The cost is 75 lakhs. So I cannot go and crash 10 75 lakh cars to do this test. That's where computer came into picture. Computer replaced physical experiments. They said, oh, you don't need to physically crash a car anymore. You can actually do it on a computer. Okay. Now, what you need to mind there is, even the computer simulations are expensive when you want to do something of a car crash or a bird impact on an aircraft engine. That's why we have put something called expensive simulations or experiment. But before that, for what combinations of this XI do I do this simulations or experiments? There is something called a design of experiment. Okay? That's what those small dots are. Getting these small dots are not expensive. They are just some combinations of x1 and x2. There is a strong statistical theory behind it. There are different techniques that are used for design of experiment. You can use whatever design of experiment that might work in that particular domain. At each of those points, you run the experiments or the expensive simulations, and you will get a response at each one of that point, meaning for each x1 and x2 combination. So this is 0.1, this is 0.2, this is 0.3, this is 0.4. For each of these points, I have to go and run the simulation and I will get y1, y2, y3, y4. Okay, now what will I do with that? What I can do with that is I will be able to approximate the y using a function f. Actually, I'm representing it as f hat because it's not the actual function f, but it is based on the data. It's a data-driven model. So I can approximate this function f using some simple techniques that you might already know. I'm just showing it in ND. If I have a bunch of x and y, do you guys know how I can find the relationship between X and Y. There is something called curve fitting, line fitting, regression. Even in simple Excel, you can do Y equal to mx plus c. I'm sure that you have gone through that in your 12th standard or at least in your engineering. It's the same idea. The only thing is it's just not 1x, but I'll have x1, x2, x3. Okay. And we can use the same least square technique to be able to do this in polynomials, but there are also something called maximum likelihood estimate approaches and stuff like that to do that. Now, this approximation of this function f is called the metamodel or the surrogate because it's not the actual model. It's a metamodel. It's a representation of the model, right? Once I have this, I can do multiple things like I can do sensitivity analysis because I have a closed form function now. I'm constructing the supposedly f, and I call this f hat. Now, what I need to understand is if I'm going to change x1 by 2 units, I need to know how much y will change. So I can do that because I'm going to have a closed form function for f, and whatever I ask now is called the sensitivity information. Okay. Then I can do optimization. Okay. So those are next step. But the question here is, how good is your metamodel? My metamodel is only as good as the number of DOE points that you have and the locations of your DOE points. How many DOE points do I choose for 5 dimensions? It depends on the nonlinearity of your design space. It depends on how nonlinear is my output function. But how do I know that? Well, I need points to know that. How many points? That again depends on the function nonlinearity. So this is a chicken and egg problem. That's why we have put this cyclic stuff. It's not a forward problem. It's a cyclic problem. One result influences the other. Okay. Now, this is what we called as design space exploration. Even before someone wants to build a metamodel or a function approximation, you want to have a fairly reasonable understanding of what the design space is. Okay. So once you are able to do that, then we can do, as I pointed out, sensitivity analysis, or you can visualize. What I mean by visualization is, can I see where the peak is, meaning maximize? Can I see where the valley is, meaning minimize? Can I see where the function is flat, meaning robust design? Or you can do an optimization study. But the thing is, all this, beyond this 2 dimensions of x1 and x2, I cannot show you this picture. I cannot show you this picture because I myself don't know how it looks like in the hyperplane. But if I show you this picture, from the picture, you can tell me that this is where the minima is, this is where the maxima is. And these are regions where it seems like it is flat. It's sort of all of them are yellow in color. That's going to be the robust design. So this is something that we want to do for n dimension. Stay with me. Now, the function nonlinearity governs the model choice, the type of kernels used in your metamodel, the number of samples, and it's a cyclic problem, as I pointed out. And in higher dimensions, whether it is conceptual design or in the multidisciplinary concept, we want to identify the sweet spots, right? So I told all that. Now we'll get into the next part, which is what are the existing techniques that are available. So I just shown 3 things here. One is called the nested access plot. The idea of nested access plot is there are 4 variables in this plot. X1 takes particular values. Okay. This entire thing takes a value of 1 in X1. And in in X2, it takes a value of -2. But within this particular stuff, X3 and X4 are varying. Okay. So you get it? So there are 4 variables I'm representing. X1 and X2 are fixed. Within each tile of that X1 and X3, X2, I'm actually having contours of X3 and X4. Okay, just give me a second. I need to just give me a second. Sorry, I'm back. So we are talking about nested access plot, where 4 variables can be represented in the same plot. Okay. I hope you guys are with me, right? So if the question is where is the minimum of this function, if you can see this color legend, you can tell me that this is a low value, right? Wherever the blue is deep, that's the low value. If I want to know where the high is, this is the high value, and I go look for those colors. And this tells me that this is going to happen somewhere at 0 of x2 and x1 is -2. But what is the value of x3 and x4? It is the whatever their lowermost values are, because well, not lowermost. It's similarly in the central values of x3 and x4. Okay. Now this is good, but the point is, if I want to know for values of x1 equal to let's say -1.5, then I have to go and do another, because right now my x1 and x2 are fixed. My x3 and x4 are varying for different values here. But if I suddenly ask what is -1.5 x1, there is no plot here. Okay, so this is good to look at the space, but it doesn't give you like specific values. You'll have to repeat these plots if you want them. Tile plot is very similar. x1, x2, x3 are fixed, and x4 with respect to x1 is varied, and x3 with respect to x1 is varied. So this sort of gives 1:1 comparison. Okay, but however, my x1 is fixed. It's not, x1 is not varying. x1 is fixed. Now, if I want a different value of x1, then I have to go and change that. So it means that if I want like 5 values of x1, I need to have 5 such plots. Parallel axis plot comes from the data analytics people. It's interesting. There are different varieties of this, but the problem is these are your coordinate values. These are the different stuff. You can see even with 4, how you don't know where this line is going. Okay, it's coming something like this. Okay, so it becomes cumbersome to follow. Of course, there are interactive graphs, like you can click and then it will highlight that. But even then, making a decision is slightly difficult. Okay. Now, these are all good for up to 4 to 5 dimensions. There are also other stuff like bubble charts, scatter plot, generative topographic mapping, but all this come at a higher computational cost. Oops. We propose using something called a self-organizing map to be able to do this. So the idea, I'm directly jumping into the idea, what it does. So we start with the design of experiment, which is nothing but a set of points. So let's call this x1 and x2 if you want. So for different combination, that comes from statistics part, some statistics. Okay. Now, what happens is each of this node, I'm going to have something called layers. Oops. Now, each of this point is mapped to a layer. So there is some layer in between, there is some layer in between, and this point is mapped to the last layer. So how many ever samples I have those many layers. If I have 100 points, I will have 100 layers. What are these layers? The layers are nothing but they are just, because if I take this one, there is an x1, x2 in this, but then I can also have xn, right? So that's what we have written here, x1 to xn. And the y is a corresponding response. At each of this point, you also have a response. So I have this. Now, I am mapping each one of this data point into a layer. Each point becomes a layer. Then what do? There is something called a grid. Imagine there is a grid like this. You have seen meshes, right? So imagine that there is a mesh like this. Okay. Now the mesh, you have seen these meshes in garden, the green color mesh, it will have like a net. Now this net can bend. Imagine that part. Okay. Now, each of this net here, the connecting point is called a node. Okay. So each node is connected to all the layers. Now, what does this? Each node will get weights, okay, for every layer. So now, wherever I have marked W1, if you see, the W1 is not a value. It is not a deterministic value. It is a vector, it's an array. What does it say? It says M11, M12, which is for the different, the weights that is associated with the inputs first, and then for the output. Okay, this is for layer 1. Now you go to layer 2, the node 2, then this is W2. Then I will go across different stuff, and this guy is called the J, 1, 2, 3, 4, whatever it is, and this is J. And the same story will hold good for J as well. And N is the number of design variables and out. So if I had multiple outputs, then I will have M1 out separately. Then I have W1 separately for M2 out. Okay. Now this is called the node or the map. Now what we do is, this is how you construct. Okay. So this is a very simple construction. This is just representation of the data. That's all we have right now. Now, next is, how am I going to change this node or this map to represent my function? What am I going to do? Imagine this is a 5-dimension place, A, B, C, D, E, F, 6-dimension space. And these red dots that you see, these are the data points. And this is the map that we constructed just now. Now I need to move this map some way so that it goes and maps itself to these points. So just stay with me, simple. How does that happen? I find out the distance of each node with respect to the points that I have. So for the first point, when I do that, I figure out that this particular node is the closest to this data point. So I pull that node towards the data point. When I pull that, what happens? The neighboring nodes also get pulled towards it. Now next, I go to point number 2 and I repeat the same stuff. And then point number 3, and then I keep doing. Finally, I started with a map like that, and I end up with a map like this. So it bends and scales up to the function values. Now what I can do is this: in every axis, I can project and I can get that. So if this was A, dimension A, then this is a self-organizing map of the component plane. Component plane means that variable space is called the component plane. The component plane map of A. Similarly, I will have a component plane for B, C, D, like that. Okay. Now, how do I interpret this map? Just stay with me. Don't worry about the text there. I'm going to use the, because at the end of the day, this is a visualization technique, right? So you should be able to visualize. Imagine this simple function x squared plus y squared. It goes like this, right? So you all know. It sort of goes up to the top 4 corners and the minima is somewhere there in the center, 0, 0. Now, this is passed through a SOM mapping tool, and these are the results that you get. The component plane XY and the output Z. Now, how do I read this plot? The point is simple. Actually, this Z should represent this, but in the conventional SOM, that is the C SOM, it's not necessarily true that it captures the shape of the function, at least explicitly. Inherently, it does, but not explicitly. Now, how do I read this? So let's say that you are interested in the minimum values of Z. So from this color legend, you can tell me that this is the minimum value of Z. But if I need to know at what values of X and Y will I get that, the similar point or the geography where I'm looking at in the Z, I go and look that in the X and Y as well. So for these values of X and Y, I'll get the minimum. What are those values? So you can see that this color is somewhere here, which is close to 0. This color is somewhere here, which is close to 0. So typically at around 0, 0 is what you are getting the minimum values of Z. How good are these? It's only as good as the DOE points that you have. But the point is, the advantage of this is you can do this for any dimensions. I'm showing you this in 2 dimensions. But if you had like 25 dimensions and you'll have an X25 component plane, of course, you'll have X24, X23, X20, all those, and then you'll have a Z. Now, interestingly, you can also say for what value of Z, what will be the different combinations of Xi. Okay, I hope you get that and you stay with me, right? Now, what we are telling is this is not very interpretable. Okay, yes, you are able to get this, but it's not very intuitive. So there's no way that I can connect this Z to the plot that I have in the left. So instead, we come up with an approach called the interpretable sum. And why we call it interpretable is because it's inherently understandable. What is desirable? So as you can see, X is increasing in this direction and Y is increasing in this direction. So if I have a component plane like this, where I can say X is increasing in this direction, Y is increasing in this direction, Z is sort of representative of this. At the center, it's a valley, and at the corners, it's a peak. So this sort of gives me that this is how the trend of the function is and the variables are, right? So we propose the algorithm to be able to do this. This is the output of our algorithm. And I'm showing you what this algorithm is. What we do is there is something called the best matching unit. You remember we did this. then this node which ties to this data is called the best matching unit. Out of this 8 by 8 data points, this is one data point that goes close to the data. The data, that particular node is called the best matching unit. What we do here is, while we are trying to, in the ISOM that we propose, what we are doing is we are not actually moving this data. Okay, we are not moving it, we are not pulling it towards the data. Instead, what we do is we just choose it as a the best matching unit, and we keep it. We don't pull it yet. Then what we do is we move all this data as the best matching unit. Okay, and then we just, you see here, these are the best matching units, right? So then what we do is along the value, we just pull it. So what happens is, when I'm finding the best matching unit, I don't take the output value into account. I only take the input values. And after I find all the best matching units, I just push the best matching unit data, the nodes, to the value of the output. So that it takes the shape. The topology is preserved and the value is also preserved. There is a small difference in the update rule between the conventional sum and the interpretable sum that we are talking about. So here is the result for the same example of x squared plus y squared. The function is varying in this direction. The function is varying in this direction. Then x is varying in this direction. Y is varying. So if I want minimum y, minimum x, minimum z, sorry, I will have to select some points here and here. So if I want maximum, I can select any of the 4 corner points. Y is minimum, y is maximum, x is minimum, x is maximum, x is minimum, x is maximum. Any of these combinations will give you the extremes, the lesson. So what we are saying here now next is, like, this is another example. It's called a camelback function. It has like 6 minimas, local minimas. There is one global minima in that. So these are all sampling based approaches where you want to do this. You really want some very good sampling around this region to be able to capture this, but we don't know that a priori. That's the assumption. Instead, what we do is we do a budget. We say there are only 40 simulations that you can do. We take 30 simulations to understand where the region of interest is. And in the region of interest, we'll go and sample additional, and then we'll be able to build a better refined meta model. So how do we do that? With the initial 30 samples, we are getting this sort of a representation. What will be my interest? My interest is this guy, minimum. So I will just say my design space is reduced. So the remaining 10 points I will only put in these regions, and I will get more points in this region in addition to the original. And then I'll be able to. So this is a starting. So you can see the range is -2 to 2. Then I reduce to the space, which is -1.5 and comma 1.3. And with the additional number of points here, 21 points plus 9 points initially, I'm able to build a better meta model with a very good metric. This is nothing but an R-squared metric. And I'm able to get a pretty close optimization result that is already presented with a lot more samples. So this just says how many samples are used, right? So we are proposing somewhere around, this is about, this up to here is the C sum, the conventional sum, and this is our approach. So roughly at about 40 samples, whereas in literature you can see 100, 200 samples, someone has used 45. And we also provide something called a topographic error and quantization error, which tells us like how good our approximation is. Then we extend this to other examples like the heat exchanger, which is a standard problem in our domain. The point that you need to note here is, like, we are going to higher dimensions, x1. It's the same idea. We start with a larger range, and then I go to a smaller range, and then I use like additional samples, a better meta model, and I'm able to get quite a nice optimization result. Then we go to a 6 variable high concrete strength example. So there are 6 dimensions, because please understand the power of this method lies here. Irrespective of the number of dimensions, you can get plots like this, and you can even compare. Okay, so for instance, you can see that these 2 variables are very similar, x3, x2, and x4. You can see that it's increasing in this direction. Okay, and you can see that this guy is flipped. It is going in this direction, and in this case, he's going in this direction. Sorry, in this direction. This is flipped. Angle-wise, it's flipped. And you can say that x5 and z, okay, probably xy will influence the z the most, because it looks very similar. And for your kind information, there is no technique so far which can give you this sort of information. And imagine that this, if you can do this for 30 variables, you can do this for 100 variables. Of course, you cannot do it with naked eyes, but you can do this using some simple image processing techniques. Okay. So in that sense, the power of this approach is like fantastic, especially with the ISOM, because we sort of regulate how someone can look at the data. Okay. So it's the same thing. That's why I'm skipping. There is something called a U matrix, which allows us, if you build this, it permits you multiple things. One of the things is the cluster, right? Clustering stuff. So what this does is, it takes the maps W1, W2, and then it introduces a cell between W1 and W2, W2 and W3, W1 and W4, W4 and W5. So it introduces all these, the orange colors, right? So it is, the orange ones are called U12, which means it gives you the distance between U1 and U2. Between U1 and U4, I have U14. So that gives me the distance between U1 and U4, node U. So 5, this 5 is connected to W2, W3, W6, W9, W8, W. So now each one of that it will have, if you see, W2, 5, U3, 5, then U5, 6, then U4, 5, then U5, 8, then U5, 9. Okay. Now it gives you, all these guys give you the distances of U5 with respect to the neighboring nodes. Now, what does this tell you? If U2 and U3 are far away, then this guy is going to have a larger value, which means it will have a red color. If U2 and U3, U5 are close, then this guy will have a low value and it will give you a blue color or a green color depending on the value. Now, this is very useful because you can see discontinuities in your data, in your function. Because what does discontinuity mean? There is a point with a low value, and right next to that, if there is a point that has a high value, then the function is called discontinuity. And that's exactly what this U matrix captures. And it also says, if the function value is not changing, then most of these orange cells will have like similar values in that region. And you can say they all belong to a particular cluster or a particular patch. Okay. So this is a simple stuff that I just wanted to discuss. We have been using this for other things such as Pareto front visualization and large data graphical optimization and stuff like that. So we are using it for robust optimization. We are using it for n-dimensional problem. Function of spacing in DOE, because many times the question is how many points will you use and how good this output is. The output is only as good as your DOE, but how good is the DOE? So we are saying that can we rate the DOEs to begin with and then say with respect to this rating of the DOE, this is the function, this is the confidence that you have. And there is something called quantifying uncertainties. This is the uncertainty that is associated with the inputs. You can, it might mean just bounds, or it might say the values are random and they follow particular distributions and stuff like that. So this is something that we are currently looking at. You can just search for my name, PALANIAPPAN RAMU, and it will take you to my webpage, and we keep updating the publication, so you can go and see there. With that, I'm technically done with my talk, and I'm okay to take questions.
Students, kindly post your questions in the chat box. Professor will answer that.
So, so have you used these maps in anything recently?
Sorry?
Have you used this technique to solve any optimization problem that came out? Real life thing.
Yeah. So for instance, the two examples that I showed you, the high strength concrete and the heat exchanger problem, they are actually real life problems. But currently we are working with Professor Kalyanmay Deb from the University Michigan State University. He is Kalyanmai Deb is on the other extreme, right? So he's the founder of NSGA, non-sorting generic algorithm. Okay, and if you look at his citation numbers and all that, it is like some 1.5 lakhs, like 1,50,000. Okay, and just to give you an idea, is if you look at my numbers, they are under 1,000. Just to give you an idea, okay. And then my mentor from University of Florida, who's no more, is one of the very well cited person in our domain and all that, has somewhere around 35,000 citations. Just to give you an idea, okay. Now, if this guy stays at like 1,50,000, so we are working with him to look at Pareto friends. Pareto friends is something called trade-off curves.
The 80-20.
Well, that's the Pareto rule.
Pareto rule.
This is called the Pareto curve, which means there is a conflicting. Pareto friends are very interesting stuff in life in general, because anything that any decision that you make in life is actually conflicting. It is a trade-off decision, right? So it's a trade-off. So what I'm going to do is I'm going to share my screen so that I can explain a little bit on what that guy is, so that you have a better understanding. Hey. Okay. So let me use this. It's my class note stuff, but still it's okay. So, sorry. So let's say that you have this graph, right? So this is your quality, let's say, and this is your cost. Now, what happens is, if you want a better quality, then your cost will go up. Okay. So what you actually want is, you want to reduce your cost and still you want to better your quality. So there is a curve that goes like this. Am I right? Or should it be the other way?
Other way, maybe.
Well, yeah. I mean, what is happening is your quality is decreasing and your cost is...
No, the other way.
Yeah, so the cost is decreasing. So we'll have to have this way. So if my... No, the quality is increasing.
The mirror of that first thing that you did.
Okay. So I should have it like this.
Like this, yeah.
So this is your quality and this is a cost, right? So now what happens is, usually you don't get a graph like this. If you get a graph like this, game over. Okay. So there is something called a knee point. You want to do this. You want to know this. Because what will happen is, for a small or for a large change in my quality, because I'm going to increase my quality from here to here. But then my cost change is very less. But for my quality change from here to here, I have a large cost. So this, especially in n dimensions, is very important to visualize. And it's not possible. Until we went, they were able to visualize, and they were able to visualize this in 3 dimensions. Only in the objective space, function space. But now with our approach, they are able to go back to their XI, which we call the decision mapping. So we are able to do that in real life problems. And yeah, and there is, I don't know if you know Aishwarya, so she's looking at something called farmer producer companies. So she's doing some organic farming farmer producer company and the other one. And we are able to look at the data across 60 different farmer producer companies and say whether leadership skills or buying potential, which are the attributes that contribute. So we are, to answer your question, yes, we are. And here are some examples of some cases where we are using it on a real life basis.
So will it mean that curve delta that you showed, where the quality dramatically increases, that is our sweet spot as well?
In a Pareto curve, yes.
Yes. Okay.
Because that's where the designer would love to know, right? Like, if I can get so the initial cost is, you'll have to incur that cost, but beyond that you'll have to invest a little bit, but then your quality goes up like anything. Okay. It could also be the inverse. It doesn't mean that, see, for instance, if you want hush puppies, yes, you'll have to give 3,500. That doesn't mean that if I'm going to give 4,500, I'm going to get a far better slipper or a shoe than that particular brand. Hush puppies is just an example. Okay, I have no preference over that. I'm just giving you an example. So it is important to know how much are you going to gain for whatever you invest. visualized. And this is true in everything that you look at.
Yeah.
Yeah. So, for instance, why I told that this is very applicable in our real life is you play multiple roles. Like, for instance, you'll have to take care of your health. You'll have to finish your stuff. Okay. Now, what happens is the more the time you spend, it doesn't mean that you are productive. After a certain time, you're not productive. Your productivity goes down. So that's actually a trade-off that you need to understand. So if you put a graph, then you will know like after 6 hours or 7 hours, your productivity is coming down. So it's a trade-off. So you'll have to take a break and go work out, So yeah, so
Balance
that's
it, yeah.
Yeah. So, and it's true for everything that you do. You'll only have like so much of investment, but you'll have to put it in mutual funds. You'll have to buy a apartment. You'll have to buy a vehicle. You'll have to invest for your health and all those things. So you make a trade-off. So trade-off is what life is. Trade-off is what design is. So it's very, very applicable to life in general. There are no more questions. I never thought that
Professor,
she's
there is one question in the chat box.
Where is it?
Can I read it for you, sir?
Yeah, read it.
Students from KSR IET has posted.
Someone called Dilip. Oh.
Not that, sir, before that.
Okay. No, okay. Before that, there is nothing. Done. Raised hands. That's it. I don't see any.
Can I read it for you, sir?
Student everyone. KCG, Roshan.
No, they are putting their attendance. Before there is one question.
Chat. Okay, wait.
Yeah. Can I read it, sir?
When SOM is suitable compared to other AN? Is that the question?
Yes, sir.
I'm not sure what do they mean by other AN. And actually, I don't understand this question.
This is a question from the faculty. Professor, do you want to elaborate on this?
You can put him, you can unmute him, probably.
Yeah.
Hello, sir.
Yeah.
Just I want to know, I'm faculty from KSR Institute for Engineering and Technology. So for compared to other artificial neural network, so what is the special about SOM?
There is nothing special. This is just artificial neural network.
So for which kind of applications this will be more suitable?
For visualizing your stuff. If you're only looking at multidimensional, any n-dimensional visualization, you can use this. And what I'm saying is the classical SOM that I showed you in the beginning, it has some issues of aberrations and all that, which I did not go in because it's slightly detailed. What will happen is the map can go because you will randomly pick your nodes. So if you pick node 1 and then you go to a point, then you pick your node 2 here and then you go to the next point, it might go and cross itself like this. So what happens is that affects your visualization. So imagine that your I don't know, just hold on. So this is the sheet, right? So the first node goes here. Now imagine the second node should go there. Instead, it went like this. It folded itself like this. Okay. Then when you visualize this as a projection, you will not see it like this, but you will only see the projection of this. And that gives a misrepresentation of the data. Okay. But actually that's not correct, because if you take the points, it will be correctly mapped. But when you're projecting the structure, it doesn't take it that way. So what we do in the interpretable sum is, as the name suggests, the output is directly interpretable. As I showed you, you don't need to be super smart to look at it. You look at it, this is how x1 is varying, this is how x2 is varying, this is how x3 is varying, and accordingly my y is varying. So it captures the shape of the original shape of the function. It is again only dependent on the number of DOEs you use. DOE points that you use, but it gives a very good representation of the corresponding input variables. So to answer your question, for visualization purpose, you can use this.
Okay. And for which kind of simulation or which type of tool you have used for this, if I have not missed the session content? For visualization?
You mean the software that we have used?
Yes, sir. Yes, sir.
SOM is there in almost all for instance, you can go to R, you can go to Python, you have a SOM toolbox. SOMPy in Python, and R, you should have an equivalent stuff. MATLAB has a SOM toolbox. If you go to my webpage, we have a paper, probably 21. In that, we will have our own code. okay, which is again a modified version of something that is already existing in MATLAB. But you can get as many codes as you want. SOM is a reasonably established approach.
Okay. Thank you so much, sir.
Sure, welcome. Anything
Dilip
else?
has raised his hand. Dilip, do you want to ask any question?
I think he accidentally raised his hand.
Yeah, because I asked him.
There are many other faculty members available in this session. Do you have any questions?
Man, this is interesting. 135 people. Let's say about 10 of them are organizers.
No. 5.
Okay, doesn't matter.
Yeah.
10, 20, still 100 people are there.
Yeah.
I'm going to randomly pick people and ask. Kamalesh,
Yeah, that's the way it
KCG,
is.
Kamalesh.
Lamna, you have to keep up the speed and unmute that person so that.
Unmute, ma'am. I have opened it
Yeah,
up.
yeah. Kamlesh. Sure.
He refuses to unmute. He or she, I don't know. Monica Benjamin. She's a student.
She's also a KCG person.
Yeah, KCG.
Shiva Sharvesh. 3 people escaped now. 135 became 132. Shiva Sharvesh.
No, I think they should. You should put your video on so that we can take a picture of you. When I come to your institute, something will ring a bell.
I don't know. These people have not listened to me, right? Like if you guys have listened to me, you know that I always have a surprise. Whoever can answer, you will get a surprise.
Yeah.
I am wondering. So KCG, maybe I have not spoken. KCG is our in Chennai, right?
Yeah, it's in Chennai, next to that Karamba.
Yeah. I don't think I visited them.
They're very smart lot. I think 100 of them registered.
Of course, all of them. Oh, is this only from KCG?
No. We
Okay.
have from different places.
Okay.
I saw Professor Nagappan from Savita University. He's a RAC member.
What is VCEW?
Vivekananda College.
Vivekananda College of Engineering for Women. It's an exclusive college only for women.
Where is this?
This is
Coimbatore.
in Namakkal.
Namakkal.
Tiruchengood. Yeah.
Tiruchengood, okay. Okay, all right.
Wait. Let's pick
Professor,
some.
there is a
Sure.
question in the chat box.
Okay, hold on. I'm losing. I actually, okay, chat is there. To what extent can we translate this concept to SLAM? I don't know what a SLAM is. Can you either type or unmute yourself and say what is SLAM? Too many terminologies these days. Bharatram. LISET is what? Laila Institute.
Yes, sir.
Yeah.
Simultaneous mapping and localization. I don't know. Is this a GIS technique or something? I don't know what this is, so I cannot comment. But it's interesting. I don't know what this is. Simultaneous mapping and localization. Does it sound similar?
I think that sounds more real time than yours.
Can you unmute me, ma'am? Boy, this guy is curious. Please unmute.
Bharatram.
Yeah, you can unmute Bharatram.
Good evening, sir.
Sure,
So-
please, Bharat, go ahead.
SLAM is nothing like to generate the map for robotics actually. So
Yeah, it looks like it's a dynamic update, right?
yeah, it's a dynamic update. Like you estimate the post and correct the path. Because
I guess you can use this. Yes, I mean,
the problem in SLAM is the way we are representing is not like very easy to do it, or like condense the data and represent it. It's very difficult.
yeah, I really can't comment because I don't know what SLAM is.
Oh, okay, sir. Thank you, sir.
Yeah, thank you. Dear sir, can you give the students a purpose of using this software? How to develop by getting these skill challenges? Can you give the students a purpose of using this software? I thought that was the purpose of this talk, right? So to visualize data, you can use this, okay? This is not a software, meaning like you can write this code in any software that you want. We have, I mean, for instance, we have something in MATLAB, but you can write it in Python, or some of them is already available in R. So the purpose is to visualize data. Any data you can visualize. We are using it for exploring the design space. We are also looking at some market data for someone, time series, but that is sort of like 1 month old. We haven't gotten a hold for ourselves. But it is sure it can be used for visualizing any type of data. How to develop by getting these skill challenges? I don't know what this means. Madam, if you think you understand what it means, I can answer the second part. How to develop by getting these skill challenges?
See, first you need to understand what you're expected to do, and then what you're supposed to use as a software or whatever. So the first part is to understand the purpose, as you've mentioned. The purpose is to visualize and visualize the data, and then you should be able to juxtapose it in any kind of multi-dimensional situation. It could be time dimension, another dimension, seasonal, or whatever. And once you are able to get a hold on that kind of a thing, then you will use appropriate software. It could be Python, as you said, it could be R, or it could be anything. And
no, I mean, don't think too much about the programming part. Today, programming is like fairly straightforward, like you take any open source, most of the underlying SOM stuff is, I mean, you can start with underlying SOM. If you're interested, we have our iSOM open. You can go to that paper, and then we have a link in which you can download the iSOM toolbox and use it, right? Even otherwise, you can just write to me and I can refer you to some students, and then you can take it from them. That's not at all a problem. But I really don't know what is the second part of your question. How to develop? You mean like develop oneself by acquiring these skills? Yeah, I mean, you acquire the skill and probably try looking at visual analytics or data analytics stuff. Yeah, that's it. I'll write to you. Thank you. Will this help us understand what happens under the hood of RL? You mean reinforcement learning? This guy seems, is it reinforcement learning? Yes, sir. Okay. Well, that's an interesting question. I haven't thought about it. But I think no, because the way I'm trying to think through a little bit. Maybe not, because reinforcement learning, the way the data is basically the incentivization is the concept, right? So you get it, you get 1. If you don't get it, you get 0. Then you get 1. Then the model gets trained that way, right? So the learning in this happens in a slightly different way, because it's not 1 and 0. It says like, I'm going to get 60, I'm going to get 70. So I don't know whether we can use categorical variables, but can we use a binary stuff? I'm not sure. I don't think you can do that. If you do, you will not get so much information. Maybe not. I don't know. The answer is most likely no.
Make the question more detailed, sir. If it's I'll ask it more detailed way. Like there are policies that are employed in RL, sir. So like that decides like how we are giving rewards and as such.
Correct.
So usually we can tweak the parameters of the policy and get results. But right now we just use it as a black box. Like put some value.
For that purpose, probably yes. Because this is a very interesting question. Thanks for this question. Because currently what we are doing is we are looking at some metamodeling techniques which actually have a machine learning origin, like some sort of boosting or earth models and all that, right? The catch in all that is your tuning parameters. And there is something called an active subspace that we are trying to do. What it says is, irrespective of your number of high dimensions, there is only few active subspace, right? So we are identifying the active subspace. There is a rigorous mathematical way to do that. But what we are also doing is, the catch all these days has been the dimensions. So in 2 dimensions, if I plot, you will say, I know the function is varying maximum in this direction, so I'll approximate it in that direction. Now what we are saying is, I will allow you to plot the function in n dimensions. Then you can visualize in which dimension it is varying the most. And will that be your active subspace? We are looking at that. Okay, so that's one thing. And the one that I actually started to look at, started to answer was, we are looking at the tuning parameters. So the tuning parameters, which one to do, is actually an optimization problem if you understand how the tuning parameters are selected. So what we do is we build the SOM in that space so that I can do a visual optimization and say this is where the combination is, and you please take that. So you don't have to run an optimization problem to do that. You just have to take the data, plot it, and SOM will tell you this is where the optima is. So from that perspective, yes, it can be. So you said under the hood, it can give you input values for, yes, the tuning parameter sort of stuff in your reinforcement learning. Yes.
Trade-offs are usually based on the cost factors. So when you're dealing with multiple parameters, will you also have a cross function with the cost for those parameters?
Sorry, can you come back? I mean,
See,
can you
we
ask?
have multi-dimensional plots is what we understand, and each of the dimension or the parameter that you are considering may have different cost implications. So again, cost will be something that will drive the whole lot finally,
Right.
right?
So what happens is, it is not only the objectives, we also have something called constraints. So you can model the different cost as different constraints. That is one possibility. Or the different combination that arrives at that cost can also be modeled. So it can be a constrained multi-objective optimization. It can be. So that's one way to look at the problem. Other questions?
Participants, it's not every day that a professor from IIT will come and give us a session. So
Okay,
I'm
looks
sure
like they
all
were
of
not
you
very.
should have a lot of questions. Other than Bharatram, I'm sure there are other students from various colleges who should be having questions. So type it, feel free to type it in the chat box. I'm also seeing it in the live chat in YouTube stream. We're not having any questions there too.
Bharat, are you, which background are you? Which engineering background?
I'm an electronic and communication engineer, so PC.
Which year are you in?
I'm currently in my third year.
Third year. What are you doing this summer?
I'm looking for opportunities for internships, sir.
Okay. Are you looking for paid internships?
Not necessarily. I'm
Well,
open to.
if you're interested, just write to me.
Yes, sir. Yes, sir. I'll surely do it, sir.
If you're interested only.
Yeah, yes, sir. Yes, sir.
No obligation.
Yes, sir.
I'll most likely forget. So you just, even if you write, you need to say I attended your talk and you suggested that I write. Okay.
Will do, sir.
Yeah.
So,
Bharat, you can get in touch with us. You can get in touch with us if you want professor's email ID.
Yes, ma'am.
No, I'm that famous, I guess, madam. You can just search for my name and it will take you to my email. Okay. Can this be used in detection projects? What sort of detection? Detection could mean many things, right? What sort of detection? Malaria. Okay. Well, if you have the data, yes, sort of. In a sense, see, the point is very simple. Okay, if you have an XY data stream or if you have an XI data stream, then you can do. That is all. If you say, can I use SOM to identify malaria just like that? I don't know. But if you say that I have data, I've gone around and I've collected data and I want to visualize the data, and can you tell me like region wise or which factor is more responsible for malaria or which age group is more responsible or more prone? Those type of all those games you can play with SOM. Yes. If you have data, we can run SOM on it and you can get all sorts of insights into it. And the point is, there are a lot of other things that do, and sometimes they are even more powerful. Okay. But the strength is, what do you think the strength is? This should have been an MCQ question. What do you think the strength is? Where do you think the strength of our approach is?
Predictive.
Students, just type. Whoever it is, type. It's okay even if you're wrong. Where do you think the power of our technique is? Or the power of Psalm is? Power of our technique also becomes very specific. Where do you think the power of Psalm lies? I used this word at least 20 times. If you were in my physical talk, none of you would have gone home today if you didn't answer this question. No, not a single person. What do you think is the power of song? Not necessarily high dimension, visualizing. Thanks, Bharatram. Otherwise, I would have felt very bad. Visualization. Okay, so the point is, that's what I said. There are a lot more techniques that might actually do better things for you in terms of like diagnosis, prediction, prescription, everything. But most of them cannot help you visualize the data. Sometimes what happens is visualization is very, very, very important. Now let's say that you take this data, the data is collected by primary healthcare analysis people, and that's something that we are trying to do with farmers and the farmer producer companies and all that, because you go and show data they don't understand. But then if you show a graph, if you show these sort of color plots and you say red is more, blue is less, and then it increases this way, they are able to appreciate that. In a similar fashion, if you go to a primary health center and then you show this data and then you ask them, then they might be able to identify trends that we might not know, and it might make more sense to them. So in that sense, to answer Naga Abhirami, your question, yes, it can be, provided you have the background data for that basic medical, or it can be anything. It can be anything. Any other questions? Comments also. Welcome. I guess PALs themselves get comments, but if you want, you can drop an email to me. You will get my email ID. If you believe that I could have made the talk more interesting by doing something or explaining something better or showing additional example, please be specific and write to me what is it that could have made the presentation even more interesting.
Yeah, PMO will post the feedback and online test link in the chat box. You will feel free to take the test and provide your feedback there, apart from writing to professor as well. It was a wonderful, wonderful visualizing experience for us without the photographs and without the pictures of those people who are attending. It's definitely a different experience, and it's a new. It's a more complication of an existing bar graph or a pie chart, a little more than that, and bringing in other concepts like constraints and pause factors. I think I personally learned a lot. Quite a lot of notes have been taken. I don't know if I'll take the test though. Thank you very much. He's popularly known as what, clone of Google Pichay? You didn't tell that. There were people who came and took selfies with him when we went to Tiruchengood last, and ASR. So definitely the real life, the physical events that we conduct have lot more reach and connect with the people. And here it is only with the names. And I hope Bharat will take it on himself to write the mail to sir. And all the KCG guys, I would have been happy if you had asked a few questions. I'll tell
Even now you can ask, come on.
Even now, it's perfectly all right. Yeah. And
you can never go wrong in a question, right? You can only go wrong in an answer. So you shouldn't even worry about it.
Our popular thing is you remain a fool if you don't ask that foolish question. please ask that question and get it clarified. So it would remain that way if you don't ask that question.
I think maximum attendance from KCG college.
I know attendance should be translated to questions as well. So I'm going to talk to Dr. Dhanalakshmi about you all.
The Dhanlakshmi is also there in the session.
Yeah, she'll know what I'm talking.
Maybe she should lead the way by asking
Yeah.
question.
Madam, the ball is in your court.
All right.
Okay. Thanks a lot. And it was a great evening, well spent. And thank you for your time.
Thank you. Thank
Thank
you
you.
for all who showed up. Okay. Bye.
Yeah.
Thank you, ma'am.
Bye.
Thank you
Thank
for
you,
the
Professor.
opportunity.
Thank you.
Thank you, Professor.
Then I end the stream without
Yeah.
forgetting.
Yes, ma'am. I want to mention that quiz thing. That's why I made it.
Yeah. Mention.
Participants, I hope all of you had a wonderful session today. We have posted our online quiz link and feedback form in the chat box. Quiz is based on today's lecture and some other general questions. It will be open for next 24 hours. Requesting all the students to take it up. The best performers will get prize or certificate at the end of this academic year. And also, please submit your valuable feedback in the given link for our continuous improvement. Both the links were mentioned in the chat box. Thank you all. Thank you, Anu ma'am. Thank you, Arundev sir.